So looking at review problems, going over percent comp first, which is this first one, calculating the percent by mass of water in the barium hydroxide octahydrate, that's what that's called. Then we're going to look at these two that are conversion ones using our lovely mole map. So I designed them to be able to flow a little bit better on this page. All right, so calculating the percent by mass of water of barium hydroxide octahydrate. Anybody have any idea where to begin here? What do I need to do? I need to find masses, good. And where do I go to find masses? Where are they located on that periodic table? Exactly right. So, oops. There we go. Here's a periodic table for us to look at. So going over here, I'm just going to list them out. Barium, there's only one barium, but if I look over here at what it's in group 2, that's 137.33. Now distribute the 2 to each here. Remember, parentheses, you distribute. So 2 oxygens, 2 times, and then if you look over here, we round it to 2 decimal places. That's going to be 16. So that's 32, pretty easy. 2 times the H, we look over here, we round it to 2 decimal places. H is going to be 1.01, so that's going to be 2.02. And last but not least, we need to look at our waters over here, and there's 8 of them. So for our water, we're going to multiply it by 8. Now in the water, it's 1.01 for the hydrogen, but there's 2 of them, so we multiply by 2 there. And then we're going to add in the 1 oxygen at 16. So I guess that's what we could do there. Did my parentheses wrong, but let's add this together. This is 1.01 times 2, which is 2.02 plus 16. So this is 18.02 grams per mole for water. So you're going to probably get to know that number very carefully because we're going to use it quite a lot for the hydrates. So 8 times that, we can start adding this up using your handy dandy calculator. So 8 times 18.02, that gives me 144.16. Is that what you got? 144.16, okay. And then we add all this together to get the entire mass. We need the entire mass because we're going to do the mass of the water divided by the entire mass times 100. So 137.33 plus our 32 plus 2.02 plus the 144.16. Did you get 315.51 for your entire mass? 315.51 grams per mole. That's going to be the entire mass right here. Now, if we put the water amount on top, 144.16, and then we multiply by 100, we will end up getting our percent. So 144.16 divided by 315.51 times 100, and let's go out 2 decimal places for the percent too, following the molar mass rule. So I'm getting 45.69%. Everybody else get that? Because I can punch numbers wrong in the calculator too. So just check and verify, please. Yay, okay, I see some people saying, yes, that's what they got. Wonderful. All right, now let's look at this next one. How many liters are there in 5.919 times 10 to the 27th molecules of oxygen? Now remember, oxygen's diatomic. It's one of these diatomic elements that is a molecule because it shares electrons, but it's actually an element because it only has the one element in there. All right, so I'm starting with molecules. From molecules, where's the only place I can go to on the mole map? What's the only place I can go to from there? when I'm converting? Molecules goes directly to what? To moles. We got to go to moles first. Everything goes to the middle where the mole is. Good. And then after the mole, we can go ahead and head over to the liters, the volume. Add STP since it's standard temperature pressure. So this one's going to take 2 steps to get there in the T-chart. So another question here. What number do I use to convert between molecules, which is a type of particle, and moles, which, of course, going to that middle value? Whose number am I going to use there? Or what number am I going to use there? Going from molecules to mole. Yep, the 6.02 times 10 to the 23rd. And then to go from moles to liters, what's that conversion factor? (22.4). All right, good. Very, very good. So we're going to start over here, starting our T-chart. Put the given information in the upper left corner. So we got, and this is molecules. I like to abbreviate MLCS, so I have to write out the entire word of O2. Okay. Then we're going to diagonal that down. This goes down here to cancel. So we put molecules O2, and then we're going to 1 mole. Remember, everything goes to 1 mole. Now the molecules number is Avogadro's number, 6.02 times 10 to the 23rd, because that's how many particles are in 1 mole of any substance. And then now we can continue on with our track. So we're going to have to take our moles now and diagonal them down. So 1 mole of O2 equals the liters of O2, which happens to be this 22.4 number. So we put that there. And if you look now, we've set it up so everything's going to cancel. I'm going to be able to cancel now. I'm going to go ahead and cancel in green. Cancels, molecules cancel, moles cancel, and then we're left with our liters of O2, which is what we want. And when you do the calculation, you get a pretty large number here. So let's go ahead. It's like, don't forget to use your second comma button for the EE, because you want to use your exponent key in your calculator so that you don't mess up the power on the 10. And I'm getting, let's see here, typing this in correctly. This is my raw calculator answer. This is what I'm showing up in the calculator. Now I'm not going to be able to keep all that because that's way too many digits. We have 1, 2, 3 sig figs. So I'm going to be able to keep 3. I'm going to go 1, 9, 3. Do I round up the 3 or leave it a 3? Leave it. Good. Okay, so what happens to the 116 place values now? What do we do with those? Since we only can have 3 significant digits, what do they become? 3. Yes, they all turn into zeros. So then they're going to be zeros. Exactly right. Don't forget your unit. Don't forget your substance. Now, if you don't like this big number, you can always change it over. 1, 2, 3, 4, 5. So this would be 1.93 times 10 to the 5th of O2. Can definitely do that. And those would be either or would be an appropriate answer to this question. All right, looking at the last conversion one. Let's try to think about where we need to start and go on the map. How many chromium-4 ions are in 192 grams of chromium-4 phosphate? Well, it has a transition metal in it, so it's a good bet. We're talking about an ionic compound that has ions in it. Obviously, says ions right here. So we're going to be able to break this up at the end. We're starting with grams. From grams, we're going to go to the middle, which is the mole again. From the mole, though, since this is an ionic compound, what type of particle would I be converting it to? Would it be molecules like up here, or is it going to be something different? It's something different. It's the formula unit. Very good. We use formula unit because remember, for ionic compounds, it's the lowest ratio between the two ions. Now, once we have the formula unit, then now we can take the formula unit, which is Cr3PO4 here, and we can break it up into its individual ions. So that's going to be where the other step comes in. This one's going to take 3 steps. 1 to do that one, 2 to do that one, and then 3 to finish it off for the ions. So I'm going to go over here and I'm going to start with my grams in the upper left corner. Okay, Cr3PO4, 4. Start my T-chart. Now I'm going to diagonal down the grams of the Cr3PO4, 4. And yes, it gets tedious rewriting the substance, but we need to do that for later on purposes. 1 mole of Cr3PO4, 4. Now, I'm going to look up this stuff on the periodic table in just a minute. We're just going to finish setting up our track. You can always go back and do the molar mass later. So I take my mole, diagonal that down here, put the mole here, Cr3PO4, 4. And now I'm going to formula units. And formula units is like a molecule type of particle, so that's going to be Avogadro's number, 10 to the 23rd. I can't even see what it's writing. It's writing so slow in comparison to me. So formula unit, Cr3PO4, 4. It's going so slow, my tablet is. I don't know why. It's like it's tuning out. Okay, sorry about that. Let's keep going. Now we're going to take our formula units and diagonal them down. So the formula unit, 1 formula unit of the chromium 4 phosphate. How many of the chromium ions are in it? Out of this formula unit, how many of them are going to be chromium 4 ions? 3. So this is where we put 3 Cr4 plus ions. So I'm going to erase this part so we can see the rest of our track now. And so forth. And now we can get ready to do the math here on our molar mass, which of course we need the periodic table for. So I'm going to do it down here. I have chromium, I have 3 of them, and chromium, if we round it, it's going to be 52, plus the phosphorus, and phosphorus, distribute the 4, phosphorus is 30.97, so 4 times 30.97. Plus now 4 times 4 here gives us 16 oxygens at 16 each. And so we go ahead and use our calculator to add all that up. 3 times 52 plus 4 times 30.97. Could easily have done that badly. And 16 times 16. So I'm getting 535.88. 535.88 for the molar mass, which we would put there. Now we can do the rest of the calculation. 192 times 6.02 to the 23rd times 3 on the top, and divide that by 535.88 on the bottom. So I'm getting here 3 significant digits for my answer. So I'm going to keep the 6, the 4, the 7, and times 10 to the 23rd. And then this would be Cr4 plus ions as my final answer with the unit and the substance. But you can always go back and check your answers here. All right, let's talk about hydrates. We're going to review a little bit from prior where we did the percent comp. and then talk about looking at how to calculate the formula and find the coefficient in front of the water. All right, so remember the hydrate is an ionic compound that has water molecules bound to it. And they're usually pretty colorful crystals, like so. These are the copper 2 sulfate pentahydrate crystals. They're pretty blue. And if you notice on the diagram, once again, before, you just have your copper ion and your sulfate ion. But in the after here, you see the waters, which are these H2Os here. They have all attracted in. 4 of them are attracted to the copper, and 1 of them over here is attracted to the sulfate into the ionic compound's structure, into its lattice. And the way we write it, of course, as you can see in the formula, CuSO4 with the dot and then the 5 in front of the water. So that, number in front of the water is going to tell us how many water molecules have been absorbed into the structure for each particular formula unit. So for every formula unit of copper sulfate, you have 5 waters bound in there. So naming a hydrate is very simple. We're just going to do like 1 or 2 examples here. You name the ionic compound just like you would regularly name any compound. Then you use a prefix for the coefficient in front of the water, and then you add the word hydrate. So it's pretty simple. So for this one is copper 2 sulfate, because we know copper is a Roman numeral 1 that has multiple oxidation. But the 5, of course, is going to be penta, and then we just add the word hydrate. So it's copper 2 sulfate pentahydrate. Here, looking at this first one, what's Fe? What's that name? Iron. Now, is iron a transition metal? Does it need a Roman numeral? Yes, okay, and this is phosphate here. So phosphate's -3 if you look it up on the periodic table. I mean, not on the periodic table, on the polyatomic ion list. This is +3, so that means this is iron 3 phosphate. So that's probably the harder part. Now, what's the prefix for 4? Tetra, so this is tetrahydrate. Tetrahydrate. How about this one? Ca is what? Calcium. And does calcium ever get a Roman numeral? No. Okay, so then this is Cl, so that's just going to be chloride. Calcium chloride, and then what's the 2? What's the prefix for 2? This would be dihydrate, like so. See, it's not that much different than what you've already done. This one would be heptahydrate. This would be trihydrate. Anybody remember what C2H3O2 is? It's one of those bigger polyatomic ions. Of course, Na is sodium. No, it's not glucose. Glucose isn't a polyatomic ion. And glucose is C6H12O6. Yes, it's acetate. Acetate is what's in acetic acid, which happens to be, the common name is vinegar. So this is sodium acetate trihydrate. So yeah, when you're eating your salad or, having your fish and chips with some vinegar, you're eating acetic acid. Has acetate in it. So you can take a look there if you want to do the other one, but that's basically, you just add the prefix and the hydrate part on the end. All right, so removing water from a hydrate. This is kind of the lab that we're going to do next class, and we'll kind of go through the video then. But basically, you're taking the hydrate and you heat it up for a while, and heating it up will make the water molecules evaporate out of the hydrate. and that leaves behind the water-free anhydrate. We call the ionic compound without the water, it's designated anhydrate. Hydrate has water, anhydrate is the ionic compound without the water. Okay, so that term, get familiar with it, anhydrate. Now this is a lot of steps, and this is why I put the steps in the notes where you don't have to write them down. You can just refer to them and follow along with what I'm doing. So basically you're going to record the mass, find the mass of the anhydrate, and then you can calculate the mass of the water. And you can do too, like you could have the mass of the water and the mass of the hydrate and figure out the anhydrate. Like you can manipulate this equation, but the hydrate minus the anhydrate gives you the mass of the water. Because essentially, what is the hydrate? The hydrate is actually the ionic compound weight plus the water weight. And the ionic compound is the anhydrate. So lots of steps here. And then like step 4, you have to convert both of your masses to moles. And then this is the only part that's kind of new, is like taking the moles of the water, dividing it by the moles of the anhydrate. And that's going to give you the coefficient that goes right before the water. You know, you have the dot and then the coefficient and then the water. So let's do an example problem together where we follow these steps. Hydrate of magnesium sulfate has a mass of 13.52 grams. So whoever's doing this lab, they dumped 13.52 grams of this hydrate into, you know, a weighing boat and put it on the scale and is getting the mass in grams. Sample is heated until no water remains. So they take it, they either use a Bunsen burner or they use a hot plate, doesn't really matter. But they heat it up for a while and make sure that all of the water has evaporated out. So the magnesium sulfate anhydrate has a mass of 660 grams. Find the formula and name of the hydrate. All right, so the first thing, once again, mass of our hydrate, I'm just going to use H, minus the mass of the anhydrate. That should be able to give us the mass of the water. So that's a pretty simple step. So let's go ahead and do that. 13.52 minus the 6.6. That gives us the mass of the water. And the mass of the water is 6.92 grams. So this is the water, this is the magnesium sulfate, the anhydrate. Now that we have both of those, what you need to do is you need to take those and convert them to moles. So we're going to take these both and convert them over to moles using our molar mass. Now the water one's pretty easy because we already know the molar mass of the water. We just calculated it, which is 18.02 grams of water. That equals 1 mole. And this is going to be 0.384 moles. Keeping 3 significant figures following our data here. And remember, the significant figures are based off of the measuring tool. So this is based off of the scale or the balance going out 2 decimal places. So this is the moles of the water. Now the other one, the magnesium sulfate, 6.60, which is the anhydrate here. I'm just going to tell you the molar mass because I forgot to put the periodic table in here, but magnesium is 24.31, the sulfur is 32.06, and then of course 4 times 16 is 64. So this is going to be 120.37 grams. That equals 1 mole. So 6.6 divided by 120.37. This gives us 0.0548 moles of magnesium sulfate. Now, since we have the moles, you do something called like the mole ratio. So the moles of the water divided by the moles of the magnesium sulfate here, that's going to give us our coefficient number, that number that goes in front of the water. So 0.384 divided by 0.0584. And it should be close to a whole number. So let's see what we get here. Yeah, see, I'm getting like 7.007. Well, you know, that's really just a 7. So that's my coefficient here. So if I'm writing the formula, let me do that in a different color. So this is going to be MgSO4, put my dot, 7 waters. That's where the 7 goes. And then, of course, naming it, this is going to be magnesium sulfate. And the 7, of course, equals, oops, don't need an equals in here. I just need to write the heptahydrate. So this would be the final answer. But you need to make sure you show all this work. Step 1, finding the masses. Step 2, converting the masses to moles. And step 3, figuring out the coefficient by the mole ratio there between the water and the anhydrate. So these are kind of lengthy. There's only one problem to do in the choice board assignment for hydrates. But like I said, we're going to do a lab on it where I'm going to give you actual data. And you're going to calculate it from there, and we're going to do the lab on Tuesday. So for the last 7 minutes here, let's go ahead and look at this other problem here. It's just slightly different than the first one. Anybody, once you finish reading it, can tell me what the slight difference is from example 1? I mean, besides it being a separate, different hydrate, but it's kind of going to be in step number 1 where the slight difference is. What did they give us this time? What was our input information? Yeah, they gave us the water this time with the hydrate. So when we do the subtraction, what are we finding? So remember last problem, here, I'll go back one. We had the mass of the hydrate, we had the mass of the anhydrate, and we found the mass of the water. So yeah, this time they gave us the mass of the hydrate and the mass of the water, so we're finding the mass of the anhydrate. So if we're doing that here, we would have, you know, the mass of the hydrate minus the mass of the water. That's going to give us the mass of our anhydrate. That's simply because the hydrate is the combination of both elements, or both things together. So this would be 8 minus 1.14, and then that gives us the mass of the anhydrate. So this is 6.86 grams. And our anhydrate this time is lead acetate, lead something acetate here. All right, so now we need to convert, so this would be step 1. Now we need to take those grams and convert them over to moles. Let's go with purple. The water's the easy part, right? So 1.14 grams H2O. Convert that over, that's 18.02 grams of water. That equals 1 mole. Go ahead and do that. 1.14 divided by 18.02. So here I'm getting 0.0633 moles of water. Harder part, of course, is finding the molar mass of this because it is massive with lead in there, of course. So this is 6.86 grams PbC2H3O2, which is acetate. Oh, and there's a 2 outside here, so that means the lead must be a +2, because this acetate's -1, so it's lead to acetate. Now we need our periodic table to find the molar mass. I don't know lead off the top of my head, so I have to actually look it up. It's 207.2. Wow, it's a big heavy metal. So lead is 207.2. There are 4 carbons, so 4 times 12.01 for carbon. 6 hydrogens, 1.01, and then this is hydrogen, and then oxygen I'll put up here. There are 4 times 16. So throw that all in your calculator and add it up. So 64 plus 207.2 plus 48.04 and 6.06. I'm getting 325.3. Anybody else get 325.3? Oh, so now we can convert this over. 325.30 grams equals 1 mole. And then we can find our moles of the lead to acetate, which I'm getting is 0.0211 PbC2H3O2. Wow, that's a fun compound to write out, isn't it? Now, for the last step, all we have to do is do the moles of the water divided by the moles of the anhydrate. So moles water divided by the moles of the lead to acetate. And that would give us, it looks, I can tell by the numbers here, 0.06 divided by 0.02, that's going to be a 3. But you could throw it in your calculator and see. So then this ends up being PbC2H3O22 with the dot, 3 waters. And then the name lead 2, because we know lead is a Roman numeral 1, even though it's not in the transition section. Acetate, and then it's trihydrate.